Welcome back to Physics Made Easy at Wood Green, this week's edition on half-life. This week is a continuation of the topic we looked at last week on radioactivity, and just a very quick reminder that this process of radioactive decay is both spontaneous and random. It doesn't really depend on any other factor like temperature, for example. And there is a term called the half-life, which you will come across in GCSE physics, which is an indication of the amount of radiation decreasing with time. And I'd like to put the word average in here, the average time it takes for the activity of the radioisotope to halve. I put the word average in because it connects with spontaneous and random. And you will get a curve like this. On this curve, you will notice that it does not touch the time axis, and likewise on this vertical axis, I've used the letter A for activity, and all I've done is I've gone down to a value half of the initial activity, go across and read off the value, and then if half of a half is a quarter, and then do the same again, and you will find those gaps are roughly the same, and that term is called the half-life. We'll call that T a half. Let us just put this into practice. If you take a tree, trees photosynthesize, and they take in carbon dioxide, both in the form of carbon-12 and carbon-14, and let's just suppose a living tree has 80 units of radiation coming from it for every gram. And if we take a ship, for example, and let's just suppose for argument's sake it has got 10 units of radiation coming from it, we want to work out the age of the ship. So, you'll notice it's gone from 80 units to 10 units. And 10 out of 80 is an eighth of the initial activity. Now, to get to an eighth, you would have to halve the initial activity, halve it again, and then halve it again to get an eighth. So that's half of a half of a half, that's 3 half-lives. So this ship is then 3 lots of 5,700 years old. That will then make it 17,100 years. I can give you a second example. A second example is one, there's an isotope of strontium, strontium-90, a half-life of which is 28 years, and you want to work out how long it would take for the activity to fall to 1/32 of its initial value. Now, to get to 1/32, start with a whole, you have to end up with a half, then a quarter, then an eighth, then a 16th, and then 1/32. Probably a good idea to present it like this because you can then just count the arrows. 1, 2, 3, 4, 5. The radiation halved 5 times. The half-life is 28 years, so the time it would take to get to this fraction is 5 times 28, i.e. 140 years. I will now show you, with a very simple practical, how you can actually model radioactive decay. We can model radioactivity using these Tillix cubes. And what we've got here is that one face of this cube is in fact painted black. So if these represent atoms, and then if I place all these in the container, give it a little bit of a shake, throw them out, there's my first throw, and then all I do is I take out all the cubes face up with a black face. Remove those. After the first throw, this is the number of cubes that have been left. You then repeat the process, give it a shake, and I can then take out the ones that have decayed, the number left after the second throw, and then I'll do this one more time. and then take out the ones that have in fact decayed. And then you repeat the process again. Right, coming back to the idea of modelling radioactive decay, and you will have seen that this represents the number of throws, and this is the number of cubes that remain after each throw. And you'll notice that I've actually drawn a graph of the number of cubes remaining against the number of throws, and you get a very, very similar curve. Some of you may want to find out what the name of this curve is. Once again, I haven't got it touching the x-axis. So all I now need to do is find out what is the half throw. So for example, if I start with 120 cubes, go down to half the number, go across and read off, roughly every throw represents the half throw, or the half life. So, and likewise, if I repeat that again, it's roughly a throw that actually halves the number of halves the activity of the radioactive isotope.